Discuss about the chain rule, which is a major technique which can be used in evaluating the derivative of a function. So let's encounter what is chain rule. You have seen this and used this several times before, but for the sake of continuity and completeness, let's start with the single variable case itself. So consider we have a situation where w is a function of x, not just a function, w to be a differentiable function of x, and x can be found as a differentiable function of t. Right. So if it is the case, we can identify w as a function of t with a particular composition. Right. So in this setting, t is the independent variable, w is the dependent variable, and this x may be termed as an intermediate variable. Right. So x actually connects between w and t. So x may be termed as an intermediate variable. So if this is the case, the derivative of w with respect to t, dw by dt, is given by dw by dx into dx by dt. Right. So if you have a composition w equal to f of phi of t, where f and phi are differentiable functions of x and t respectively, then dw by dt can be evaluated as dw by dx into dx by dt. Right. So this is the chain rule for single variable cases, and as we have done before, we will be exciting this directly to the cases of higher variables or vector functions. So consider we have a function w equal to f of xy, which is a function of two variables, and let this x is a differentiable function of t, say phi of t. Again, we have another variable here, y is a differentiable function of t, say psi of t. Right. So what we have here, we have a function w, w a differentiable function of x and y, given as w equal to f of xy, and x is a differentiable function of t, given as x equal to phi of t, and y is a differentiable function of t, given as y equal to psi of t. Then from this setting, we can use chain rule to evaluate the derivative of w with respect to t. Right. This may be expressed as dw by dt is equal to dou f by dou x into dx by dt plus dou f by dou y into dy by dt. Note the changes happened here. When we moved from a single variable to two variable function, we have something new here, the partial derivatives. So when we try to find the derivative of w, which is a composition of f with phi and psi, or f of xy where x equal to phi of t and y equal to psi of t, the derivative can be found using this formula, where dw by dt equal to dou f by dou x into dx by dt, dou f by dou y into dy by dt. This expression makes sense since w is a differentiable function of xy and phi is a differentiable function of, x is a differentiable function of t and y is a differentiable function of t. And for those reasons, this formula makes sense. Right. So there is a graphical method to express this. We have w equal to f of xy. The direct variables here are x and y, and again these x and y are functions of t. Right. We move from w to x with partial derivative similarly to y, dou f by dou y, and from x to t we had a single variable function phi of t, right, x equal to phi of t. So from x to t we move as dx by dt. Partial derivative doesn't make any special sense there, so dx by dt, dy by dt. Right. So from this diagram we can deduce that dw by dt is dou f by dou x into dx by dt plus dou f by dou y into dy by dt. Okay, right. So such a setting may be called a tree diagram, and this special case we may term this as a tree diagram for chain rule. Right. So now let's see an example. Consider the function w equal to xy, w equal to xy, also given that x equal to cos t and y equal to sin t. Right. So find dw by dt. In fact, there are actually two ways to evaluate this. You can directly substitute x equal to cos t and y equal to sin t and express w as a function of t itself and try to differentiate with respect to t using product rule. That's fine. But for this case, let's use chain rule as a matter of practice. So how do we evaluate dw by dt using chain rule? So what is the expression for dw by dt? It was dou w by dou x into dx by dt plus dou w by dou y into dy by dt. Right. So let's find each term one by one. So what is dou w by dou x? W equal to xy, x equal to cos t and y equal to sin t. Right. So what is dou w by dou x? Partial derivative of xy with respect to x is nothing but y, since y will be treated as a constant. Right. So what is dx by dt? Dx by dt is derivative of x equal to cos t with respect to t, which is nothing but minus sin t. Right. So what is dou w by dou y? Which is nothing but x, since when we differentiate with respect to y, we may treat x as a constant. And what is dy by dt? Derivative of sin t with respect to t is cos t. Right. So remember the expression for dw by dt, derivative of w with respect to t, as dou w by dou x, which is nothing but y, into dx by dt, which is minus sin t, plus dou w by dou y, which is x, into dy by dt is cos t. Right. Now you may substitute x equal to cos t and y equal to sin t in this equation, which will give you minus cos t sin t plus y is sin t, so minus sin square t plus cos square t. So we got cos square t minus sin square t. So what is cos square t minus sin square t? Which is nothing but cos 2t. Right. So dw by dt is cos 2t. You can try it by substituting x equal to y and x equal to cos t and y equal to sin t in here itself and try to evaluate using product rule. You may end up with the same answer. Right. So if they had asked us to find the derivative at t equal to say pi by 4. Right. So we may try to find dw by dt at t equal to pi by 4, which will be cos 2 into pi by 4, which will be cos of pi by 2, which is 0. So it is possible that we can evaluate dw by dt at any point. Right. So I hope this serves the need. So the next question arises: is it limited for two variable case? No way. As we have seen before, every theory and every concept we explain are actually applicable for any finite number of variables, right? There may be some changes for infinite number of variables, but we don't deal with it for now. So consider three variable case. Let w equal to f of x, y, z be a differentiable function of x, y and z. Let x equal to say some a of t, y equal to b of t and z equal to c of t be functions of t. Not just functions but differentiable functions of t. So let w be a differentiable function of x, y and z, x be a differentiable function of t, y be another differentiable function of t and z be a differentiable function of t. Right. Then extending the previous formula, dw by dt can be evaluated as dou f by dou x into dx by dt plus dou f by dou y into dy by dt plus dou f by dou z into dz by dt. Right. In this manner, we can extend this chain rule to any number of finite variables. Right. So can we use our previous tree diagram to represent the chain rule for three variables? Let's have a look at it. We have a function w equal to f of x, y, z. As we have done before, we have three variables here, x, y and z. So this has to be connected by means of partial derivatives. Dou w by dou x, dou w. It's fine to write dou f by dou x as well. Dou w by dou y, dou w by dou z. And all of these three, x, y and z, are function of t. Right. So this is t. And these are connected by means of ordinary derivative, dx by dt, dy by dt and dz by dt. So this is the tree diagram corresponding to the chain rule for three variable function. Right. I think we need not go for any example for this case. You can do it. There are examples available in several textbooks and you may find it online as well. So this is how we extend the chain rule for any number of finite variables. And so far we have seen the cases we had certain number of intermediate variables, three in this case, x, y and z, and a single independent variable. Right. This may not be always the case. Like we can have two or more independent variables and many number of intermediate variables as well. So as an example, let's consider a case where we have three intermediate variables and two independent variables. By that we mean, consider a function w equal to f of x, y and z, where x is a function of, say, two variables. Let x be a function of some phi of rs. Let x be a two variable function. Let y equal to psi of rs. Right. So this makes a slight difference. We have been dealing with functions with only one independent variable, but we have two independent variables r and s here. Right. So in this case, we may evaluate dou w by dou r, what we have done for two variable functions. Right. So dou w by dou r will be dou w by dou x into dou x by dou r. Remember, dx by dr cannot be directly written since x is a function of r and s. So dou w by dou r can be expressed as dou w by dou x into dou x by dou r plus dou w by dou y into dou y by dou r plus dou w by dou z into dou z by dou r. Right. Similarly, dou w by dou s can also be evaluated as dou w by dou s into dou x by dou s plus dou w by dou y into dou y by dou s plus dou w by dou z into dou z by dou s. Right. So in this manner, we can find the partial derivatives of w with respect to each independent variable r and s. So let's revisit the formula once again. So if w is equal to f of x, y, z is a function of three variables, a differentiable function of three variables x, y and z, and all x, y, z are differentiable functions of r and s. Oh, we have forgot something. X is equal to phi of rs. Y equal to psi of rs, say z is equal to some alpha of rs. All these three functions have to be differentiable function of r and s. Right. If it is the case, we can evaluate the partial derivatives of w with respect to r and s as dou w by dou r equal to dou w by dou x into dou x by dou r plus dou w by dou y into dou y by dou r plus dou w by dou z into dou z by dou r, and similarly for dou w by dou s. Right. Remember that we don't use any total ordinary derivative here. Fine. Right. So what about the tree diagram for this case? Remember, we have two independent variables here. So first we have, give me a second. So first we have w equal to f of x, y, z, and there are three variables, intermediate variables, x, y, z, and are connected using partial derivatives, dou w by dou x, dou w by dou y, and dou w by dou z. Right. Then for now consider t, just t only, and they are connected using again partial derivatives, since x is not just a function of t but x is again a function of s as well. So we use partial derivatives here, dou x by dou t, dou y by dou t, dou z by dou t. Right. Similarly x, y, z is a function of s, so we'll have w equal to f of x, y, z, f of x, y, z. This is identical to the previous part, and we will be having s here, and these are connected by means of partial derivatives with respect to s. Dou x by s, dou y by dou s, and dou z by dou s. Right. So we use two separate tree diagrams actually for both independent variables. Right. These two together constitute the tree diagram for chain rule having more than one independent variable or two independent variables in this case. So we have seen the case where we have two independent variables and three intermediate variables between w and the independent variables, right? So now we can explain, or we can try to identify two sub cases or two limited cases of this type of chain rule application, where we have two intermediate variables and two independent variables, which means that let w equal to f of xy be a differentiable function of x and y, and let x equal to phi of rs be a differentiable function of r and s, and y equal to psi of rs be a differentiable function of r and s. If it is the case, considering the previous formula for dou w by dou s and dou w by dou r for three intermediate variables, dou w by dou r can be expressed as dou w by dou x into dou x by dou r plus dou w by dou y into dou y by dou r. That's enough. We don't have any z term here. So dou w by dou s is dou w by dou x into dou x by dou s plus dou w by dou y into dou y by dou s. Right. So this is actually a limited case of chain rule for this kind of application, and how to explain this using tree diagrams. See, I'll just give you an outline, you can try for that. Obviously, since we have two independent variables, we may need two separate sections for the tree diagram. So we have w equal to f of xy, and we have two intermediate variables, and this is for say r, and we have another section corresponding to the independent variable s. We have two variables, intermediate variables here, x and y, and s. So this may be connected using dou w by dou x and dou w by dou y, and this will be connected using dou x by dou r and dou x by dou y. Similarly, dou w by dou x, dou w by dou y, and these may be connected with partial derivative dou x by dou s and dou y by dou s. Right. So this is how we make the tree diagram corresponding to this particular case of chain rule. Right. Now we may try to, or for the sake of practice, let's see an example. See, all the examples from this section are kind of easy ones. So find dou w by dou r and dou w by dou s in terms of r and s. In terms of r and s, if w equal to x square plus y square and x equal to r minus s and y equal to r plus s. Right. So the question is to find dou w by dou r and dou w by dou s in terms of r and s. In terms of r and s, where w is given as x square plus y square and x is given as r minus s and y equal to r plus s. Let's write this as other side. So x equal to r minus s and y equal to r plus s. Right. So let's recollect the expressions for dou w by dou s and dou w by dou r. So dou w by dou r is equal to dou w by dou x into dou x by dou r. Right. So what is dou w by dou x? The partial derivative of x square plus y square with respect to x, which is nothing but 2x, as y or y square itself acts as a constant when we differentiate with respect to x. So the derivative of x square will be mattering here. So derivative of x square with respect to x is nothing but 2x into dou x by dou r. Dou by dou r of r minus s, which is nothing but 1. Right. See, we have missed a term here. Dou w by dou y into dou y by dou r. Right. So what is dou w by dou y? The partial derivative of w with respect to y. As we have done for x, it is 2y into what is dou y by dou r? Again 1. Right. So which is nothing but 2x plus 2y or 2 into x plus y. So we have given x equal to r minus s and y equal to r plus s. So x plus y will be r minus s plus r plus s, which will be 2r. S and minus s will be cancelled. So this means 4r. Right. So dou w by dou r is 4r. And what about dou w by dou s? Dou w by dou s is given as dou w by dou x into dou x by dou s plus dou w by dou y into dou y by dou s. So what is dou w by dou x? We have seen 2x into dou x by dou s is negative 1 plus dou w by dou y is 2y into dou y by dou s is 1. So that's equal to 2y minus 2x or 2 into y minus x. Using the information that y equal to r plus s and x equal to r minus s, we'll get 2 into r plus s minus r plus s. Right. Which means r and minus r will be cancelled out. So 2 into 2s is 4s. Right. So dou w by dou s is 4s and dou w by dou r was 4r. So now we have expressed dou w by dou s and dou w by dou r in terms of s and r. Now find a little more special case of this where we have only one intermediate variable, which means let's consider a function w equal to f of x, where x is a function of r and s. See, when we say a function, we by default mean that f and phi are differentiable functions of corresponding variable or variables. Right, means f is a function which is differentiable function of x, or phi is a differentiable function of r and s. If it is the case, then dou w by dou r is given as, try to reproduce the previous formula where we had dou w by dou x into dou x by dou r. But since f has only one variable, does it make any sense to define a partial derivative? No, since we use, for that reason we may use the ordinary derivative here, dw by dx. In fact, the partial derivative of w with respect to x and the actual derivative, the ordinary derivative, coincide here. So dw by dx into, but the case here is as similar as before, dou x by dou r, and dou w by dou s is nothing but dw by dx into dou x by dou s. Right. Then immediately, how does the tree diagram look like? We have a function w equal to f of x, which is of a single variable, and we have only one intermediate variable, which is x, which is connected by means of the normal derivative or ordinary derivative dw by dx, and we have two independent variables r and s. We don't use two separate diagrams here, since we can successfully represent in a single diagram, so which may be connected using partial derivatives dou x by dou r and dou x by dou s. Right, so this is how the tree diagram for this special case looks like. Right, so we were actually seeing narrowing cases of or very special cases of chain rule of this type. Now let's move a little more general. Suppose we have a lot of intermediate variables and a lot of independent variables. Right. Suppose we have a function w equal to f of x, y, z, comma, etc. some v. Right. That could be any finite number. Where all x, y, z, etc. up to v are functions of say p, q, r, etc. up to say some t. Right. That can be any finite number of any finite number. Right. So what do we have here? We have a function given as w equal to f of x, y, z, etc. up to v, and each of these intermediate variables x, y, z, etc. up to v are again differentiable functions of p, q, r, etc. t. Right. So we don't have any restriction on the number. We just say any number of any finite number. Right. If it is the case, then how do we evaluate dou w by dou p? Right. We may evaluate the partial derivative of w with respect to any of these independent variables. So as an example, let's try to evaluate what is dou w by dou p. Let's reproduce the previous formula, which is dou w by dou x into dou x by dou p plus dou w by dou y into dou x by dou p plus etc. plus dou w by dou v into dou v by dou p. Right. Similarly, you can try to find the partial derivative with respect to any variable, any independent variable, by simply replacing p with the required variable, one at a time. Right. So this is actually a mere generalization of the previous concepts we have been discussing so far. There are a lot of exercises available in your textbook, and you can find a few, or at least one from each section from your textbook, and solve them as your own. We may not have enough time to discuss all of them. So now one last topic for this session, which is implicit function and implicit differentiation. Suppose we have a function w equal to f of xy, where y is an implicit function of x, which means y can be identified as a function of x. Right, implicitly. We may denote implicit function in a special form, like w equal to f of xy equal to 0. You will see why we do this. If we try to find an example for an implicit function, say x square plus y square minus 16 equal to 0 is an implicit function. And again, x square sine y plus x equal to 6 is an implicit function, since you can identify y as a function of x here. Right. So consider w equal to f of xy equal to 0 for as our general representation is an implicit function. Right. So how do we find dy by dx from this? We have seen that y is defined as a function of x implicitly. So can we find dy by dx out of this? We can make use of chain rule. So what is dw by dx? Using the concept of chain rule which we were discussing so far. So dw by dx is dou f by dou x into dx by dx plus dou f by dou y into dy by dx. Right. So since the only independent variable here is x, if you have any doubt, you may refer to the part of chain rule for a single independent variable from today's session itself. Right. Now we have certain interesting things here. W equal to f of xy equal to 0. Right. Which means w equal to 0. So dw by dx has to be 0. So 0 equal to dou f by dou x into, what is dx by dx? 1 plus dou f by dou y into dy by dx. Right, which means dy by dx equal to minus dou f by dou x divided by dou f by dou y, provided dou f by dou y non-zero. So whenever you write a denominator, make sure that it does not comes equal to 0.